Good morning to everyone. Today we are going to prove intermediate value theorem and define the concept differentiability, and we solve some problems. Intermediate value theorem. A function which is continuous in a closed interval takes every value between its bounds at least once. So, listen, a function which is continuous in a closed interval a comma b. We know that a function which is defined on a closed interval a comma b is bounded. That means the function is bounded above and bounded below. So, let capital M and small m be supremum and infimum of f of x. We know that supremum is always greater than infimum. That means m is less than capital M or capital M is greater than small m. Both are true only. If you change the places, less than becomes greater than. See the proof. Let f of x be continuous in closed interval a comma b. I already explained. Then f of x is bounded. Bounded means f of x is both bounded above and bounded below. So, least upper bound exists, greatest lower bound also exists. Here I am taking least upper bound as small m, greatest lower bound as small m, least upper bound as capital M. We know the relation between these two, that is infimum is always less than supremum. That means greatest lower bound is always less than least upper bound. Now we are choosing a value k. This k is also real number. Here m and capital M are also real numbers. A and b are also real numbers. In between small m and capital M, so we can write m less than k less than capital M. K is any real number between infimum and supremum. Now we want to show that in the closed interval a comma b, consider any point, that is C. We want to show that f of c equal to k. Then the theorem is proved. So now we want to show this concept. By the known theorem, a function which is continuous in a closed interval attains its bounds. It follows that there exists at least one point x1 belongs to closed interval a comma b such that f of x1 is capital M, and similarly x2 belongs to closed interval a comma b such that f of x2 equal to small m. If we consider x2 here, if we consider x1 here, the value of f of x1 is capital M, the value of f of x2 is small m. M is always less than capital M. Okay. Now consider a new function, that is capital F of x, and is defined as capital F of x equal to small f of x minus k. Now this capital F of x is continuous in closed interval a comma b because f of x is continuous in closed interval a comma b. K is also constant. Constant functions are continuous functions. Continuous function minus continuous function is again a continuous function. Therefore, capital F of x is continuous in closed interval a comma b. Also, f of x1 equal to replace x with x1. So, x with x1 means RHS becomes f of x1 minus k. But we know the value of f of x1, that is capital M minus k as it is. Now we have a relation m is less than k less than capital M. For example, 7 is less than 11, 11 is less than 13. From this example, capital M equal to 13, k equal to 11, m equal to 7. So, capital M minus k, that is 13 minus 11 is 2, which is positive. So, capital M minus k is positive whenever this relation is true. Similarly, replace x with x2, then LHS becomes f of x2, RHS becomes f of x2 minus k. So, f of x2 is, we know, that is m minus k. Again same values, m is 7, k is 11, so minus 4, which is negative. That's why we are going to get negative value here. Observe, f of x1 have positive value, f of x2 have negative value. Again, here also we are going to use known theorem, that is, if f of x is continuous in a closed interval a comma b and f of a and f of b are of opposite signs, then f of x vanishes at least one value of x equal to c, closed interval a comma b. That means c is a point in closed interval a comma b, that is f of c equal to 0. So now this is a known theorem. The same situations now we have. Here capital F of x is continuous. Here small f of x is continuous. Here f of a and f of b are of opposite signs. Here f of x1 and f of x2 have opposite signs. So we can use the conclusion of known theorem. So capital F of x vanishes at least once in closed interval x1 x2, which is subset of closed interval a comma b. That is, there exists a point, here you can take x1, here you can take x2. F of x, there exists a point closed interval x1 comma x2, which is subset of a comma b, such that capital F of c equal to 0. This is the conclusion of known theorem. By using this conclusion, we can write capital F of c equal to 0. Now, capital F of c equal to 0 means replace x equal to c. Then we are going to get f of c value as small f of c minus k equal to 0. So, negative quantity goes to that side, that means RHS side, then it becomes positive. So, our aim is to show that f of c equal to k. Therefore, k being any number in between m and capital M is attained by f of x at a point c. That means the value of f of c is k. Therefore, the theorem is proved. Now, we move on to new concept, that is differentiability. Now we are going to define derivative of a function at a point. This is the definition. Let f of x be a function defined in a domain D. This is subset of real number system. X naught be any point in D, then limit extends to x naught, f of x minus f of x naught by x minus x naught if it exists. That means if we are going to get finite and unique value for this limit, then we say that the limit value is called the derivative of f of x at x equal to x naught. The derivative of f of x at x equal to x naught is defined by f dash of x naught. The derivative of f of x at x equal to x naught is denoted by f dash of x naught. So, f dash of x naught equal to limit extends to x naught, f of x minus f of x naught by x minus x naught if it exists. That means the limit of this one is finite and unique. Then we say that this value is the derivative of f of x. Next definition, left hand derivative. We are already familiar with left hand limit. There also we write x naught minus. Here also we are writing x tends to x naught minus. This one is does not changing. So the value of limit extends to x naught minus f of x minus f of x naught by x minus x naught is called left hand limit of f of x at x equal to x naught and is denoted by L f dash of x naught. Now the definition of right hand limit derivative, this is also similar to RHL. There we write x naught plus. Here also we are writing x naught plus. The value of limit extends to x naught plus f of x minus f of x naught by x minus x naught exists, then that value is called right hand derivative of f of x at x equal to x naught. It is denoted by R f dash of x naught. Next, we have some important points. F of x is said to be differentiable at x equal to x naught if and only if right hand derivative and left hand derivative both exists and are equal. Then only we say that f of x is differentiable. Second point, f of x is said to be differentiable over the interval I if it is differentiable at every point of interval. Third point, a function f of x is said to be differentiable at the end points of the interval a and b, that is closed interval, if r f dash of a and l f dash of b both exist. That means this is called right hand derivative at the left end point of closed interval a comma b and left hand derivative at right end point of the interval both exists. Then only we say that f of x is differentiable at the end points a and b. Next we are going to prove a theorem. If a function f of x is differentiable at x equal to x naught, then it is continuous at x equal to x naught. That means If a function f of x is differentiable, then it is compulsory continuous. At the same point, observe, here also x equal to x naught, here we have x equal to x naught. Proof. So now we are going to considering this concept and we are going to prove this concept. Proof. By data, f of x is differentiable at x equal to x naught. Then by the definition of differentiability, we can write limit x tends to x naught, f of x minus f of x naught by x minus x naught exists and is equal to f dash of x naught. Now I am going to find this value, limit x tends to x naught, f of x minus f of x naught. So in the RHS, we are multiplying and dividing with x minus x naught. Observe, if we cancel these two terms, then we are going to get this one only. That means value does not changing, the form of RHS is changed. So observe, now I am going to apply the limit for this term and this term separately. So then we are going to get this step. Now observe, this value is equal to f dash of x naught. Whenever we are replacing x with x naught minus x naught is 0. 0 into anything is 0. So the limit of this function, that means f of x minus f of x naught is 0. Now we are going to apply limit separately in LHS. Then limit x tends to 0, f of x minus limit x tends to x naught, f of x naught equal to 0. This one I am going to write as it is, but this one is f of x naught only. Y means f of x naught is constant. The limit of constant is constant only. In the next step, this negative quantity goes to RHS side. Then we are going to get f of x naught. So from this one, we can easily say that f of x is continuous at x equal to x naught, because this is the definition of continuity. Originally, what we have, limit x tends to a, f of x equal to f of a. But here, instead of a, we have x naught. So whenever this is true, we can say that f is continuous at x equal to a. In the similar manner, we can say that f is continuous at x equal to x naught. Therefore, we can say that every differentiable function is continuous at the same point. That means differentiation at the point, continuous at the point must be same. Note, the converse of the above theorem is not true. That means every continuous function need not be differentiable function. What we proved in the previous theorem means every differentiable function is continuous function. But the converse is need not be true. For this, we are considering one example. Here we have defining f of x equal to mod x, that is minus x for x less than 0, x for x greater than or equal to 0 is continuous. This function is continuous, but it is not differentiable at x equal to 0. Continuous means how we are going to show? LHL equal to RHL equal to f of 0. Now we are going to show this one LHL. Limit extends to 0 minus f of x equal to limit extends to 0 minus f of x is mod x. While doing LHL, we are taking less than quantity, that is minus. So 0 minus. Now I am going to replace x with 0 minus h. Now the limit x tends to 0 minus changed as h tends to 0. 0 minus h means modulus of minus h. Modulus of negative quantity is h only. If I substitute h equal to 0, then we are going to get 0 as LHL. Similarly, RHL, limit extends to 0 plus f of x equal to limit extends to 0 plus f of x is mod x. Now I am changing the limit x tends to 0 plus to h tends to 0 by replacing x by 0 plus h. 0 plus h is h mod h equal to h. Limit h tends to 0, h is 0. So RHL is also 0. LHL equal to RHL equal to 0. That means limit exists. Next, observe the definition. Whenever x equal to 0, f of x equal to x. That means if x equal to 0, f of 0 is 0. So LHL 0, RHL 0, f of 0 0. So three quantities are equal. Therefore f of x is continuous at x equal to 0. Now we want to show that f of x is not differentiable at x equal to 0. For this, we want to find out LHD and RHD. From the definition of LHD, we can write limit extends to 0 minus f of x minus f of 0 by x minus 0. F of 0 is already we know that is 0 only. So f of 0 is 0. F of x is mod x. Denominator x minus 0 is x. So observe the definition. X tends to x naught minus f of x minus f of x naught by x minus x naught. Here we have x naught value 0. That's why wherever x naught we are substituting 0. Then we are going to get this step. Next, changing the limit x tends to 0 minus 2, h tends to 0 by replacing x by 0 minus h. We know that modulus of negative quantity is positive. 0 minus h is minus h. h get cancelled. Then we are going to get minus 1. Limit of a constant is itself. Therefore, LHD value is minus 1. Next, RHD. RHD means Rf dash of 0 is limit extends to 0 plus f of x minus f of x naught by x minus x naught. Here also x naught is 0. So replace x naught with 0. Then we are going to get this step. Now I am going to change x tends to 0 plus. So f of x is mod x. F of x is mod x. F of 0 is 0. So mod x minus 0 is mod x only. X minus 0 is x. Now I am changing x tends to 0 plus 2, h tends to 0 by replacing x with 0 plus h divided by 0 plus h. Modulus of 0 plus h is h. 0 plus h is h. h get cancelled. Then we are going to get 1. Limit of a constant is itself. That's why limit h tends to 0, 1 is 1. LHD value is minus 1. RHD value is 1. Therefore, LHD not equal to RHD. Whenever these two quantities are not equal, then we say that the function is not differentiable at that point. Here the point is x equal to 0. So, the f of x equal to mod x is a function. This is continuous at x equal to 0, but it is not differentiable at x equal to 0. Therefore, we can easily say that every differentiable function is continuous function, but every continuous function need not be a differentiable function.